Let's determine the shape of some common molecules. This oftentimes goes by the name valence shell electron pair repulsion theory, and it's a very learnable thing because it follows a lot of logical progressions. What would be the shape of something that is just one atom? I think it would be spherical, right? Just one atom, have a spherical shape. But what if we had an atom attached to one thing? I think its shape has to be linear. What is the shape of something that is an AB2 system? Well, they spread out as much as possible. That's the assumption we'll always make, is that things will try to spread out as much as they can. That would be a linear shape. How about something that has three things attached? The farthest they can spread out is still linear, and we call this trigonal planar. However, now let's start saying, what if one of them was a lone pair of electrons? That means it occupies that space, but it isn't attached to anything. This is equivalent to just Xing it out, right? It would then become bent. What if we had four things attached to a substance? They can do better than 90 degrees and flat. They can become tetrahedral with 109.5-degree bond angles. Let's start replacing each one of these with lone pairs, essentially removing one of these lobes. One lone pair would be just like a pyramid, right? This is called a trigonal pyramid. If you remove two of them, it results in a bent structure. Okay, we're now up to four attachment points. When you have four things attached, no, I'm sorry, five things attached, sorry. Five things attached, we now have this shape here, and it's a little bit hard to see what this thing is. I don't like this drawing that much because to me that lobe should be bent a little bit. They should be 120 degrees on this surface here, if you will. We call this a trigonal pyramid, meaning a trigonal pyramid up here and a trigonal pyramid down there. Convince yourself that it's so. Ooh, this is so much better. Can you see this one? There's your pyramid down there. There's your pyramid up there. This is a trigonal bipyramid. When we start attaching lone pairs, always attach them to the central atom on this surface here, right? Not on the top, but on this surface here. And when we do that, this now is called a sawhorse. I like to call it a seesaw. Can you see that if you rotate this over, one kid sits there, one kid sits there? That's a seesaw. If you take another lone pair instead of a bond here, we're removing two of these. So let's imagine we're moving this one and this one, only keeping that tiny one in the back. Can you see that it's now T-shaped, all 90-degree bond angles? And finally, if all three of those are lone pairs, well, it's linear. One more, octahedral substances. Six things attached to a central atom. The best they can do in terms of shape is to be 90 degrees everywhere. We call that octahedral. Replace one of them with a lone pair, and hopefully you can see that that is a square pyramid. Rotate it over, you should see a nice sort of Egyptian pyramid. Two of them are lone pairs. Make them as far away from each other as possible. After all, they repulse each other, and it's a flat structure. It's a square planar. Three lone pairs, always remove them from this, sometimes what I call a landing pad. That works for you. And you see that now goes T-shaped, and when they're all lone pairs, it is linear. This is valence shell electron pair repulsion theory, better known as shape.